So we will start today. We will see with the MOSFET. So with the scaling, charge sharing between the source and drain, and drain induced barrier lowering or punch through, and channel length modulation. These four factors we will see for the MOSFETs today. So what is scaling and all these things, and why do we need scaling of the MOSFET? So we will see these things. Okay. So if you have seen the miniaturization of the devices is possible because of the smaller in size. The devices are smaller in size. How? So initially, if we see in 1970s, these were of 30 micrometer of the device size. So now it has come to currently it has come to around 4 nanometer node. Okay, and if that is happening, so if you see that there is voltage uh, E is equal to electric field is equal to voltage divided by the length or the distance between these. Or if there is a parallel plate capacitor, you have applied a voltage V over this. Okay. So what is the electric field in between these two will be determined by E is equal to V by this length or the D. Okay. So that is the electric field. If the distance between these two parallel plates is less, then the electric field will be very high. Okay, so the same thing happens when you apply when the device size shrinks. Okay, so when the device size shrinks, so this is source, this is drain. Okay, let me take this one. So this is source. Okay, this is drain. So in between these two, this there is some distance between them. That is the channel length. Okay, that channel length is denoted by L. If this if the whole the size of the transistor shrunk, so this L, the channel length will also shrunk, right? The distance between source and drain will also shrunk. So the electric field E will be very high, right? And in that case, according to that, we if you are doing that channel length modulation or anything what scaling you are doing, so there are some points that you need to take care about. Okay, so what is scaling? Scaling is the device dimensions shrunk down. Okay, so we are doing a miniaturization of the devices, right? So that is the thing. Source and drain depletion width are comparable to the channel length. So if you are applying some voltage here, let us say uh, in this one, if we go, uh, we will come next one, I guess, because if we go back, that will be difficult. Okay, in the next one only, if I show you in this one, if you are up uh, decreasing this length, right? Decreasing this length, there is some depletion region associated with this one. This depletion WD. Okay, this WD. Okay, if you have shrunk this channel length to this one, this much, so it will be so this uh, depletion region will be that much only. It will be of equal thickness, right? L thickness. So your your device will be on without any effect of the gate. Okay. The same thing we will come next one, but just I am telling you. So you need to decrease this as well, that channel width as well. Not this depletion region as well, because if you won't decrease this depletion region to this much, so there won't be any point of scaling down. Okay, you need to decrease this. Okay, accordingly you need to dope the semiconductor, then only you can decrease this one. Accordingly you need to apply the voltage here. Okay, accordingly, you need to apply the voltage between source and drain. Accordingly, you need to apply the voltage at the gate. So, how can you do that? That we will see. Okay, and departure from the long channel devices. Departure from the long channel devices is so this your output and transfer characteristics won't be the same for this. So there will be channel length modulation. Channel length if let us say this was your channel length L, okay, and 1% of this channel length was the depletion region initially. Okay, so if we go here in this one, so in this one, this was your channel length. Okay, this was your channel length, and only if you see at this position, only 1% of your channel length was the depletion region, so that it won't be that much effective. Okay, that won't affect. If you decrease the channel length to this much, so it will be like 50% of your channel length is the depletion region only. Okay, that will affect. Okay, that will affect. So it will also affect the your output and transfer characteristics. Okay, so and also this gradual channel length approximation also fails in this one. Okay, so according to this only we have done the this output and input these characteristics that we have derived the equations, no? Output and input characteristics. So they were based on the gradual channel approximation. Okay, so and undesirable electrical behavior. So there will be some if you change the electric field or you change the voltage, so that will be different. It was earlier. So electrical behavior in the sense your output and transfer characteristics will change. Definitely will change because of the shrinkage of the channel. Okay, VDH is no longer constant with L, that we will see with the equations, and ID will no longer scales with the 1 by L. We will see all these things. Okay, so whenever you are doing the channel length modulation, that it is done according to the your electric field, constant electric field scaling. Okay, your electric field in the device should be constant. If let us say L was 3 micrometer, okay, now your L is 1 micrometer. So electric field, initial electric field was 10 raised to power 4, 4 volt per centimeter. Okay, initially. So for this one, now again your electric field in the device at this position in between these two or these here, the electric field should be the same, 10 raised to power 4 only. According to that, you need to apply the voltage.
Sir,
Yes,
am I audible, sir?
yes, you are audible.
Okay, sir, you say that your electric field will be V by distance,
V by L.
L. L is the
Mhm.
channel length. Huh?
L is the channel length, yes.
So then, sir, there was a network issue there. I cannot hear the properly, sir. From that, if you can repeat one more time, sir, it will be better.
Which one?
Sir, from the first slide, you say that E equal to V by D.
Yes, V by D.
D is the distance between two capacitor plates, sir.
Anything. If you have two contact pads, then it is the contact pad as you have source and drain. Okay. The electric field in between these two.
Okay, sir.
Okay. It can be anything. The electric field in the sense electric field in your device at any point. That should be same. I'm telling about that thing.
Okay, sir. Okay. Then,
That's it, all these things we will see in the further slides. So,
okay, then you said say that device dimension will be shrunk down.
mhm.
reverse dimension will shrunk down due to the length is reduced.
Yes, yes, dimension is the length only, length, breadth, whatever it is.
Okay.
Hmm.
Okay, sir.
We
Okay.
are shrinking the device. That means we are shrinking the length, breadth, and if we are applying the if initially if we were applying 10 volts, we cannot apply the 10 volts again. If we will apply the 10 volts again, then the electric field will be very high because if you for 3 micrometer, let us say channel length was 3 micrometer, your electric field was 3 by 10 by 3 into 10 raised to power per meter percent no, per meter. Let us say we will take it as per meter into 10 raised to power 6. So it will be 3.33 into 10 raised to power 6 voltage per meter. Okay. For
Yes, sir. Yes, sir.
for this one. So if you apply the this to one volt to 1 micrometer channel, okay. If you will apply 10 divided by 1 into 10 raised to power 6, how much it will be? It will be 10 raised to power 7 voltage per cent per meter. Okay. So it is 3 times more than that. The this electric field. Okay, if the electric field is too high, then velocity saturation. Have you seen that a velocity saturation happens? No, that right?
Yes, yes, sir. Yes.
There will be
So,
some
sir, so, sir,
other impacts.
if
Okay,
the
1 minute, 1 minute. Yeah, there will be some other impacts can come into the picture, like impact ionization. Very high electric field will be there, then impact ionization can happen, and your if your characteristics are going up and up, and it will shoot up. Your device current will shoot up suddenly because of the impact ionization. Okay. If you have heard about the impact ionization data. Now come.
okay, sir. So, sir, if the channel length with anything is reduced, we
Hmm.
have to apply less voltage because of we have to operate in the actually active region. Otherwise, it will be
Not
breakdown.
active, not active reason. I am saying if you will go beyond certain voltage, it will break down. There will be some other effects will come into the picture that we will see in the further slides.
Okay, sir. Okay.
Yes. Now, so now we will see these parameters, whatever these parameters, they will not scale because these are some constants. Okay, these won't scale with that. That is kT by Q. This is the thermal energy. Okay, it won't scale. And easy, the band gap doesn't scale because these are the material properties. Okay, VBI and phi s for onset of the inversion do not scale. So these are some of the things, and there are some other effects that will come into the picture. We will see okay, so this was the gate dielectric. Gate dielectric generally in initially it was used, let us say 300 nanometer it was used. Okay, so now you have shrink down down this your device. So let us say 10 nanometer you came. So the thickness of the 10 nanometer, the current through this gate, okay, current through this gate will be more in that case. Okay, that is the gate leakage current. Thinner the dielectric, it won't withstand with the voltage that you are applying at the gate. Okay, so there will be a gate leakage current. So, okay, let us say if there is a capacitor, okay, if there is a capacitor, so initially there was air in between these two plates. You have applied some voltage and it can store the charge, right? Now you have inserted some dielectric in between these two. Okay, this is the same dielectric here. Okay, if you inserted some dielectric, now you can apply some voltage. If you decrease the thickness of this dielectric, what will happen is there will be a current flowing through this one. Okay, this is the same thing. The current will flow. It won't withstand with the higher voltages. Okay, so that is the gate leakage current. That is the leakage via tunneling. Okay, and source drain series resistance increases, that we will see, because we will be reducing this one. We have to modulate this one. The n plus plus doping, we have to modulate this one. That will be of less doping. Okay, that will be of less doping, and that's why there will be a higher resistance of that source and drain. Okay, and channel doping can't be increased indefinitely. Okay, okay, if you because we are decreasing this doping, to reduce this width. Okay, if you have seen the you have attended my lecture on there was I have shown the aerial charge concentration, right? There was a PN junction. This is the PN junction, and there is some charge. Okay, charge associated with this. So this is minus x1, this is plus x2, and this is acceptor Na minus, and this is Nd plus. So this one, my x1 into Na minus is equal to x2 into Nd plus. Okay, and this is the depletion region. Okay, this is the depletion width, x1 plus x2, or you can say minus xa or plus xd, whatever you want to say, wd or anything. But what I want to tell you is this width, this width depends on the doping on the another side. This is the PN junction. Okay, this is the PN junction. This is the P doped. This is N doped. And if this one is highly doped, N plus plus doped, what will happen is the depletion region that is in N region will be very small, but the depletion region towards the P side it will be more. Okay, so that's what I want to tell you. That the
Sir,
same. Haha.
sir, whatever you tell that, so if I increase the doping, depletion will be reduced.
If you
At
increase
least
the doping, the depletion region in that
which will be reduced.
material. Okay, so let us. This is N plus. This is N. Okay,
Yes,
this
yes, sir.
is actually P, not N. This is N plus. This is P type material. That's why there is this depletion region width, right? This is the PN
Yes,
junction. In the previous class, I also told you why it should be P and it should be N plus, because whatever channel we are creating is N channel we are creating, right?
yes, sir. Yes, sir. You told me.
Huh.
So,
So
sir, I just want to ask you that
mhm,
you say that WD, the
mhm,
portion of WD doping
mhm.
will be reduced.
WD will be reduced in this one if you increase the doping in this N plus. Okay, so the depletion region is in both the P and N material, right?
The P will be more, sir.
P will be more if you increase the doping.
Yes,
Okay,
sir. Yes, sir.
if you increase the doping in N, it will be very less.
Okay. So,
Okay,
what is our objective, sir? We have to increase the doping towards the inside and decrease the
no.
doping towards the side.
If you increase the doping in N side, the depletion region width will increase. You cannot increase it much. If you increase the doping here, so it will be very difficult to turn on the gate. So you have to apply more voltage over the gate. So to make it N type, right?
Yes, sir.
So to create the channel in that case will be very difficult if you increase the doping here. Okay. So in that case, what we need to do is let it be as it is, P and A. Okay. But
Okay, sir.
we can reduce the doping in this one so that we can reduce this this width, this width.
Okay, okay. Okay, sir. So in that way, sir, we can reduce the gate voltage.
Which one? Aha, we can reduce the gate voltage if you decrease this, decrease the
Okay, okay,
doping
okay,
here.
sir. Okay.
Okay.
So turn on will be faster.
Yeah, you can, in another case, you can decrease the gate voltage by reducing this thickness of the dielectric. Initially it
Yes,
was,
yes, sir.
let us say, 100 nanometer. Now you have reduced it to 10 nanometer. That it will be reduced by 10 times. Okay, the electric
Yes,
field
sir.
will be increased by 10 times.
Okay, sir. Okay.
Hmm.
These 2 points I've got clear, sir.
Okay, so the scaling factor, these are the scaling things. So uh, electric field, this E is we have kept one. We are not scaling electric field. So this is the constant electric field scaling. Whenever we are doing the scaling, we need to keep in mind that it is always done a constant electric field scaling. Okay.
Sir.
So now if any length in this channel, let us say this is the channel length. Okay. So
Okay, sir.
to make it, let us say you are scaling this by a factor of k. So length you have decreased by k. Okay, you have decreased by k. Okay, so now you have not decreased by you have to let us say k is equal to 2. Okay, L by 2 you need to keep. Okay, by that
Okay.
factor you have to do. So now according to that, which other parameters, how you will voltage and all these things, the doping, how that VD applied at the train. So all these factors you also need to scale according to that. Okay, you have.
Okay, sir. Okay.
Huh. So the D is, let us say, D is the thickness of this dielectric layer that you have to scale down by 1 by K. Okay.
Okay, sir.
And RJ is the RJ is this this thickness. The thickness the thickness of the drain, the N plus doping. Okay, or this thickness also, these both thickness you have to decrease by 1k, these both thicknesses. Okay, if it was 5 nanometer, let us say 5 nanometer, now you need to decrease it by 2, divide it by 2. Okay, now VT, your VT is, I think, threshold voltage or what they are giving that, uh, I need to see.
Sir,
But
VT means threshold voltage, sir.
Wait, but okay, I have written VTH that cannot be scaled or does not scale. So that I need to see. That VT is something, I think this is the turn on voltage or something.
Sir, it is limitation because, sir, there is written that off current is off current. So I think turn on voltage is there, sir.
Maybe turn on voltage or something. So, okay, leave that part. But what you need to do is, okay, that drain voltage that you need to scale it by 1K, 1 by K. Okay.
Okay,
So,
sir. Okay.
so these are the, like NA doping. We are we need to increase this doping by K times so that you can decrease this as well. Okay. So
Okay, sir.
all these parameters are interlinked actually. Okay, all these parameters are interlinked. When you solve the problem regarding this, then you will understand better. But you just need to see that always done at the constant electric field scaling. Okay. And
Okay, sir.
according to that, you need to decrease all whatever length, whatever it is that you need to scale down by 1 by k. So if you are scaling down by 1 by k, that length, so according to that, you need to change the doping, you need to change the voltage, and all these things are okay.
Okay,
Now,
sir.
charge sharing between source and a drain. Now, these affects when you have done the scaling. So this was your device. Now it is very small. Okay, that this length is very small. Let us say 1 micrometer. Okay, 1 micrometer is there. So your source and drain. This is source, and this side it is drain. When you apply the drain voltage D at VD, so what happens? There will be some electric field. Okay, because this is N type, drain is N type, this is P type, so there will be will be some depletion region that we have seen, right? So there will be some depletion region, right? This one, WD.
Yes, sir. Yes, sir. Yes, sir.
Okay, so as you apply the voltage here, so the when you apply the voltage here without source and drain, okay, you haven't applied initially, you haven't applied any voltage at the source and drain, so there will be some flat this depletion region will be there, right? So
Yes, sir.
as you apply the drain voltage at this point, so there will be some depletion region in this one. So that depletion region without gate was supposed to be like this, right? But
Sir, you say that without gate, it will look like from starting from the gate,
yes,
silicon dioxide to the.
it should be like this. Got
Okay,
this
okay,
point?
okay, sir. Okay.
Huh. But when you
No,
apply
why,
the
sir? Why, sir?
okay, because depletion region is the PN junction, right? It will follow this path. So it will
No,
be
you can apply voltage in the gate.
when we apply the gate voltage, so it will be it okay. So when you apply the gate voltage, so it will be also this. Okay. So in that case, if you can see this dotted line after application of both gate and this drain voltage. Okay. So
Okay, okay, okay.
this is the your depletion region. Okay.
After applying gate and drain, both.
After applying both gate and drain, because of
Okay,
gate it will be like this, and because of drain it will be in this region. Okay,
okay, okay, sir. Okay,
so
okay.
you applied the gate, there will be some charge there will be both will share some charge in this region, right?
Yes, sir.
So we do not know which so because of that, okay, because of that, if you do not apply the drain voltage, it was like this, right? Now
Yes, sir.
this charge is generated by drain voltage only, so you have to apply lower gate voltage to create the channel. Okay, because already some charge is already uncovered by this drain voltage in this region. Got the
Okay.
point?
Yes, sir. Yes, sir.
So
Sir,
mhm,
uh, sir, you say that uh, with the help of drain voltage, we
mhm.
can reduce the amount of gate voltage to
Yes.
conduct the.
Yes, but for
Okay.
longer channels, it is like negligible. But for shorter channel, it is sufficient. Okay, not
Okay. Okay.
I don't know the word, but it is sort of comparable, we can say.
Okay.
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 It is enough to create. So if you decrease the channel length, if you decrease the channel length much and much, so this charge sharing will be more. The percentage of charge sharing will be more, right?
Yes, sir.
This percentage of charge sharing will be more, so the gate voltage will be reduced with the or threshold voltage. We can say the threshold voltage will be
Accessible reduce.
reduced. Okay.
Okay, sir.
Yes. So that we will see in this one. Okay. So this is the charge sharing. Okay. So this part, the red part, can you see? This is your drain contact. Okay. That is doped with N plus plus. Okay. And
Yes,
this
sir.
WDM, this thing is your after application of the drain, this is your depletion region. Okay.
Okay, sir.
This WDM, this is after application of the gate voltage. Gate voltage, this is the your thickness of the of this depletion
Channel,
region. Huh?
channel.
Yes, in the
Channel thickness.
channel thickness we can say. Okay, or depletion region in that. But in this region, these both are sharing the charge, this and this. So this charge is shared, right?
Yes, sir. Yes,
So
sir.
because of that, if your let us say this channel length was L. Okay, this channel length was L. Now it is L minus this delta L. L minus delta L. Okay.
Okay, sir.
So this is L dash. Okay, this is the thing.
Okay, sir.
Now
Okay,
the
sir.
effective channel length is L dash. So this starts from here till here. Initially it was this from this to this. Okay, this is the channel. Huh. Okay, now hmm, so in this one, so if you see this charge is forming sort of a trapezoid.
Yes. Yes, sir.
Okay, and the threshold voltage is lowered because of the this charge sharing. Okay, got the point?
Sir, sir,
Mhm,
I just conclude one point, sir. This is
mhm.
trapezoidal due to the register sharing na, from source to drain. There
Uh,
will be a different value of resistance at the distance is far.
mhm.
The resistance will be goes increase.
Which one? From where?
Yes, trapezium is formed, sir. The
I
trapezium shape is formed.
ha ha
Here, sir.
ha ha.
Due to the potential difference between in source, gate, and drain.
Mhm.
That's why this is straight line will be going to some downwards line is there.
Okay, these lines you are telling about.
Now this is a straight line will be when we are not apply any bias,
Ah, okay.
and
Mm-hmm.
the WDM above the WDM line there will
Mm-hmm.
be trapezium is formed. You say that trapezium is formed that in the channel.
Ha ha.
This is due to the means applied voltage. There will be some gradient is there, na?
Yes, that will be there when you apply the drain voltage too much. Okay, that will be
Okay,
the
okay,
channel pinch off. Channel pinch off will be there in that case.
okay, okay, okay.
Huh. That we will come into on. Okay, that we will come on. And these lines are because of the electric field, because of the electric field. These lines are the electric field lines.
Okay,
These lines, whatever you see, the arrows, these are the electric field lines.
okay, okay.
Huh. So now the charge, will due to okay, these are the equations that you need to go through with. But if we can, because I haven't been through these equations, but you can go through. It is not required though. But you just need to know how this thing is happening. Okay. So
Okay, sir.
the reason I have already told you this thing, but you need to calculate the charge of this trapezoid. Okay, initially it was a rectangular, then it was very easy to calculate the charge that is generated due to the gate voltage. Okay, now QB, that the charge generated because of that gate voltage L plus L dash divided by 2 into WDM. WDM is this width, the
Maximum
depletion
width.
region width. Okay, hello.
Yes, sir. Yes, sir. WDM is the
WDM,
maximum depletion rate width.
yes, maximum depletion region width, that is due to the gate voltage.
Okay, sir.
Okay, now, so effective gate voltage, that because of that gate voltage, this is the QB charge in the channel. Okay, the
Okay,
charge
sir. Okay.
in the channel. So Z is the channel width. Okay, channel length is L, and Z is the how deep inside this L into W is the area, right? L
Okay.
into
Yes, sir.
Z,
Yes, sir.
L into Z
Rectangular
is,
area.
yes, rectangular area. So that is the NA is the is this NA is this
Accepted
accepted doping
density.
concentration in the P silicon.
P-type region. Yes, sir.
Okay, so that will define the how much charge is there in your this depletion region. Okay,
Okay, sir.
so this is the charge, total charge in the depletion region. Okay, so L dash will be equal to this much, so that will be something. So delta VTH they have won because initially the charge was one QB, okay, Q divided by COX, right?
Yes, sir. Yes, sir.
Q into this into Z into L. Okay, this was the VTH, threshold voltage or something. Okay, now you have to remove. Okay, it has reduced to this one because of the trapezoid formation.
Capillary portion.
Okay, so that is the thing. Delta VTH, how much it is reduced is this one.
Okay,
Okay.
okay.
Huh. So I think I don't know whether you have to. So you can just okay, learn this one.
Sir,
Okay.
put the value of QB, it will be great, sir. Put the value of QB.
QB, you have to find out the QB with this one. You have to find out the QB with this one. Okay.
Okay, sir.
Mhm. Now, so this is the effective channel length. So when I told you now, if the channel length is higher, okay, if the channel length is higher, so there is no effect of the drain voltage on the threshold voltage. Okay.
Yes, sir.
So this is the drain voltage when you have applied the drain voltage 0.1 volts. Okay, drain voltage is just 0.1 volt, and this is the channel length. Okay, so this is the threshold voltage. What will be the threshold voltage? Initially, the threshold voltage was 0.7 volts. 0.7 volts. Okay,
Yes, sir.
0.7 volt. And when you decrease the channel length, so the threshold voltage also decreases. If you apply gate this VD more, okay, you have this is the curve for VD is 3 volt. This is the curve for VD is equal to 0.1
Point one.
volts. If you apply drain voltage more, then your threshold voltage will be much lesser. Okay. For the
Yes, sir.
same, can you see this? Let us say
Same
this
gate
is,
voltage.
yeah, let us say this is 500 nanometer. Okay, 500 nanometer device. Okay, for the 500 nanometer device, when you applied VD is equal to 0.1 volt, your threshold voltage was 0.6. When you applied VD was 3 volt, your threshold voltage was around 0.3 volts. 0.3 volts. Okay, this is the thing.
Okay, sir.
Now,
But sir, if I increase the VD,
mhm.
then also the sir your depletion width will be increased.
VD, where? Okay, yes, depletion region width will increase. This depletion
Yes.
region width will increase. That's why the charge sharing will be more. So if you apply more VD at this position, your depletion region width will look like this.
Yes, yes, sir. Yes, sir.
Okay. In that case, your charge sharing will be more. So your effective length will decrease, right? L
Yes, sir.
dash.
Exactly. Exactly. LDAS
Yes.
will be reduced. LDAS will be reduced.
L dash will be reduced.
Okay.
Okay. So now let us see with the drain induced barrier lowering and the punch through. Okay.
Okay, sir.
Now, when you have applied, okay, let us go in this figure only. Okay, I'll just go. Okay, just give me 1 minute. So now drain induced barrier lowering, what happens is when you you have decreased the this is the channel length. Okay, this is the channel length L, and you have applied drain voltage so much. You are increasing the drain voltage. You have increasing the drain voltage. Okay. Now, in the previous case, if you have seen that if you are increasing the drain voltage, your threshold voltage is decreasing. If you have increased the drain voltage more, your threshold voltage will increase more. Let us say applying 10 voltage, you are applying voltage 10. So your threshold voltage will be 0. Okay,
Yes,
you
sir.
you are not applying any gate voltage. Okay, in this case, you are not you have applied the VD too much. You have gone VD. You are increased VD. Okay, in this direction, you are increasing the VD. You are getting my point.
So, sir, you say that if we increase VD,
Mhm.
threshold voltage will be more.
Threshold voltage will be very less,
Less. Yes, sir. Yes, sir. Less.
right?
It will conduct faster.
Not conduct faster. You need very less gate voltage to modulate the channel.
Uh, if the drain voltage is more, sir.
If the drain voltage is very high, okay, let us say you are
Okay, okay.
increasing,
Yes, sir. Yes, sir.
you are increasing the drain voltage. Effectively, what you are doing is you are pushing this belt at the drain, pushing it down.
Yes, sir. Yes, sir. Yes, sir.
Okay, and in that case, what you are doing effectively is this is the charge sharing. If you can see, this is the charge sharing. That same thing. Okay,
Okay,
this
okay, sir.
this is the depletion region that we are talking about. This is the WD. WD. Okay, So if
Okay,
you
sir.
apply the gate voltage that is above this one, that will also push this down, right?
Yes.
So for this one, if the drain voltage is less, so it will be at this position, right? So the charge sharing would be very less.
Okay, okay, okay.
So okay, now just give me 1 minute. You will get the point. So if you drain voltage, you increase too high so that it reaches till this point. Your depletion region reaches till this point. Okay.
Okay.
So at that point, you don't need any gate voltage to conduct the channel.
Okay.
To actually to make the channel. Okay. To invert the channel. So because that channel is already inverted in this because of this one. Okay. This is your gate. No, this is your drain. Because of that channel is already prepared. Right?
Yes,
And
sir. So sir,
Mhm,
if I increase drain voltage too heavy,
mhm.
the channel is means without gate voltage it can be turned on.
Yeah, without gate voltage, it is turned on because at this point, the barrier is already down.
Yes, sir. Yes, sir. Current leak is
Okay.
there.
Okay. Now, what you need to do is just you need to push a small voltage. If an electron comes at this position, that electron will be swept away by this electric field. This electric that
Yes.
is generated by this electric field. Okay, or we will
Yes,
see
sir.
in
Yes,
the
sir.
next. Okay, that graph I haven't shown. Okay, but this is there will be very high electric field. Can you see this thing? The more the band bending, can you see the band bending is very
Huge,
high.
huge background.
So the electric field will be very high. So as soon as electron comes at this point, that will be swept dead at instantly to this one.
Yes, sir. Yes, sir.
Okay, so
That is
when
clear, sir.
it is clear, right? So,
So
okay,
for that reason, sir, we have to apply small gate voltage.
very small gate voltage, and
Yes.
it this at this position it is not required any gate voltage because it is
No, after
already
that it is not required.
after this it is not required. It is already down. Okay, it is
Yes.
already
Yes.
down, and
Okay.
and uh, on the another hand, if you need any electron, that electron can be easily passed because it is highly doped. Okay.
Okay, sir.
This channel is highly doped that electron can easily go through this.
Okay, sir.
Okay. Hmm. So uh, you got this point, right? So let us see this
Yes.
one. Hmm. When source and drain lateral depletion width approaches channel length. Okay, source and the drain. Now we have seen with the only drain because source we are applying 0 volt and there is something. So this depletion region will always be constant. That is not modulated with a drain voltage because we are applying the drain voltage positive or negative, whatever it is, so that this will go through this side. Okay, so as soon as these both meet, these both are depletion regions in the source region and in the drain region, they meet. That is the drain induced barrier loading. Okay, and punch
Okay,
through
sir.
occurs. Punch through is the whatever is I have shown. The punch through is the electron going from at this position. Okay, that is the punch through. Got
Yes,
the
sir. I
point?
have got, sir.
Huh?
Yes, sir.
Huh?
Yes, sir. I
So
have got, sir.
okay,
So, sir,
large.
in the punch through, sir,
Mhm.
if I apply heavy drain voltage and a small gate voltage because source is not considered because there will be no modulation is there because there is apply 0 volt. So if I
Mhm.
apply small gate voltage, electron can easily move with a very fast velocity. That will
No,
call punch through.
no. You no need to apply even gate voltage. because you need to conduct channel in the lateral direction, not the vertical direction.
But sir, yes, sir, I understand, sir. But sir,
Mhm.
there will be a notch is there in the type of source. So
Which,
little bit of voltage,
yes,
there
hmm?
notch is there. So little bit of voltage is there or
Notch,
not?
notch will go off if you apply more voltage. That will go off.
Okay, okay, okay,
Okay, this is just shown. Okay,
okay.
yes. So large leakage between source and drain. Okay, so what will happen is now if your channel length is very small, okay, let us say this was the channel length, right? This
Okay.
L. Now let us say this is the channel length L. So it is, let us say you just need apply 2 volts and you have reached this position. Okay, now your electron can easily go with just applying the 2 voltage as the drain,
Yes,
right?
sir, yes,
So
yes,
in
sir.
this case, uh, and if you apply lesser voltage also, let us say 1 volt, it will be here
Then
only.
also it can pass.
So, but the leakage current in between source and drain, there will always be some leakage. The leakage current will be high in this case. If your length is small, if you increase the decrease the channel length, your leakage is the in between when you want the transistor off, but it is not off perfectly. That is the leakage current. If I show you some transistor curves, this is the transistor curve. Okay, this is the transistor curve. This is the IDVD, and these are the gate voltages. Okay, yes. So with the gate voltage you have applied, this is the gate voltage it is going. So your transistor curve is not like this. Okay, but it is like this. That is the drain induced barrier lowering because of the current is increasing indefinitely. It is not saturating actually. The saturation region is gone. Okay.
Okay, sir.
In this one, just remember this is the takeaway. The saturation region is gone in this one. Okay. And if you apply more voltage, the current will be high, more very, very high. Hmm. Okay. And
Okay, sir.
okay. Majority carriers from source electrons injected into the channel swept by the field collected by the drain. So the same thing what I told you here, it is highly doped N plus plus, right? This position. So this this is the injection of electrons in this here. Injection of electrons to to your semiconductor. Okay, from the contact source. Okay, and that will be swept, injected into the channel. That was the channel and swept by the electric field. Electric field, this is the electric field, right? I told you, swept by the electric field and will be collected by the drain. Got that point?
Okay, sir.
Huh. VD lowers the barrier near the source. That is the because yeah, this is what we have seen. This is the source. This is barrier is lowered because of the drain voltage. Okay. This is the fine subthreshold, and let us see with the subthreshold as well. Hmm. Any subthreshold. This is the okay. When you say uh, in transfer characteristics, so this is the linear curve. Okay, this is ID versus VG, gate voltage. When you apply the gate voltage, so this is the linear curve. Okay, so in log curve, what you will see. Can you see this is near to zero, but it is not actually zero. The current is very, very less. So in this case, what happens is the current goes like this. Okay, this is the log curve of the transfer characteristics. Okay, so
Okay, sir.
in this region, if you see, this will give you a linear sort of in in log plot. Okay,
Okay, sir.
this is that region linear. So if you reduce the channel length, that is the channel length, it is shown 1.5 micrometer, 3 micrometer, and 7 micrometer it is shown. Okay, if you reduce the channel length, your leakage current will be more. Okay, the sub threshold current will be high, very high. Got the point? Because because it is not even turning off because of this one. The current will be there even at lower voltages. Okay, current will be high, but in that other case, the current was not that high. So for the longer channels, so the on-off ratio, what we say, the on-off ratio is high for larger channel lengths. This, can you see this? So it
Yes,
is
sir. Yes, sir.
it is
So,
off.
sir,
Mhm,
if the channel length is sufficiently large,
mhm.
then then it will be say that minority carrier will be less. But
Where
sir, if the
minority carrier where are you talking about?
minority carrier flow leakage current, sorry, leakage current, sir, leakage current.
Leakage current will be less due to drain induced barrier. There are two
Yes,
types
yes,
of
yes,
leakage
yes,
current. There are two types of
yes, sir,
leakage
yes, sir.
current. Okay, one is this leakage current that okay, turn off current. We don't uh, say the leakage current, we say this is the large leakage between source and drain, or also we can say it off current.
Okay,
When transistor is off, this is the off current. Okay, you haven't
okay.
applied any voltage to the gate, that is the off current. Got the point?
Yes, sir.
Or when you apply at the gate, there, that is the on current, that is this one. Okay, this is the on current. Okay, so can you see
Okay,
the off current for channel is very high. So the on off ratio is less than 10. Okay, so the channel is still conducting at negative voltage, negative gate voltage. It was supposed to be off. There should not be any current in between source and drain, but there is current. Okay, so in your mobile phones, the LEDs, there are many LEDs, right?
yes,
Small
sir.
in your mobile phones, laptop, TV, or anything. So these are operated with the transistors. Okay, there is transistor that is driving the LED. Okay, so
Okay,
when you turn on in one LED, there are three mini LEDs of red, green, and blue. Okay,
okay,
so so these LEDs, red, green, RGB colors make a single LED that can give you hundreds of thousands of colors, lakhs of colors. Okay, color difference, different colors. When you change the intensity of red, green, and blue, so you can vary the colors. You can make any color out of red, green, and blue. That's what I want to say. Okay, so the
okay,
intensity is controlled with this voltage. Okay, that intensity is controlled with this voltage. So if you give more voltage, so the it will be more intense. Okay, if you give less voltage, it will be less intense, right? In this one. So let come to this side. Come to this side. If they can you see this voltage? These are the gate voltages given. Okay, this is the ID current. Okay, that is supplied to the LED. Okay, so if you have applied, okay, so I will draw one more graph. here. Okay, so let us say the ideal, let us go with the ideal characteristics. So this is ID, this is VD. Okay, drain voltage. Okay, with the drain voltage, we are sweeping the gate voltage. We are sweeping drain voltage, we are sweeping the drain voltage, and we are saying the currents. Okay, so at zero gate voltage, the current will be very less. This zero voltage. If you are increasing the increasing the gate voltage, let us say to 0.1 volt, this will be the current. Okay, the drain current. If you are
Okay, sir.
further increasing the gate voltage 0.1, let us say 5 volt, your current will be like this is the saturation current. Okay, when the channel pinch off and this comes like this, after this it saturates. Okay,
Okay.
this after, can you see this thing? This is the saturation. After this it is saturating. So this is the gate voltage that you need to apply, that you will see it will show some behavior. Leave that point. What I want to say is, when the gate voltage was zero, it was very less current. It was ना के बराबर current. It was like 10 raised to power
Yes, sir.
minus 9 amps. Okay, when you apply the gate voltage, let us say the current come to 1 microamp. When you increase more current, let us the current comes to 10 microamps. Okay, the current is
Yes, sir.
increasing. That is the saturation current. So you have applied, this is the source, this is the drain, and this is the okay, this is the gate.
Yes.
This is the gate. Okay, this is the gate. So the current between source and drain you have kept some constant to this value. Let us say 0.5 volts. VD. VD is equal to 0.5 volt. You have kept constant. Now you are just varying the gate voltage VG. Okay, you are applying VG 0 volts, there is no current. VG 0.1 volt, 1 microamp. VG is 0.5 volt, it is 10 microamp, right? So you are
Yes, sir.
increasing the current with, this is the amplification behavior of this. Okay, you are amplifying. Okay, can you see this thing?
Yes, sir. Yes, sir.
This is the amplification behavior. And you are amplifying the current. This is the amplification behavior. And this drain is connected to some LED. This, let us say, this is the LED. This is the LED. This is connected. Okay. This, when you increase the gate voltage, the brightness of this LED will increase. Okay.
Exactly, sir. Okay. Okay.
So this is the like typical your any display is connected with. Okay, and each pixel, each pixel in an LED has three LEDs. Okay, in any screen, each pixel has three LED, which is
RGB.
red, green. Okay, red, green, and blue. Okay, and behind these there are three transistors. Now there are some TFT. In TFT, these are these like this. Okay, in liquid crystal there is only one LED which is modulated by the by other some kind of liquid which is modulated by the application of the electric field. Okay, that is different thing. But AMOLED displays, AMOLED active matrix OLEDs, they have these sort of. And can you have you heard about the true black and all these things? There are more contrasting colors and all these things. This happen because of this. You can modulate all sort of intensities with these. If your transistor is good, if your LED is good, then you can go with more contrasts. Okay, contrasting colors. Your LEDs should be good. LEDs color should be like true green, true blue, and true red should be there. Okay, we in the next class I have all about these LEDs. Okay, for the next class I have lecture about the LEDs, how these things, how why do we need LEDs and photo detectors, all these things. Okay, so I have
In tomorrow, na?
yes tomorrow from 5 to 6, 6 to 7. I need to see. I think 6 to 7 there is a class tomorrow.
Okay, sir. Sir,
Yes.
sir.
Uh-huh.
So as per these two slides, whichever you told,
Mm-hmm.
in next slide, sir, next slide, graph part.
Yes.
Whatever I can understand that if the channel length is very short,
Mm-hmm.
so it can be problem to turn off the device.
Yes, it will be very
During-
difficult. So there will be always turn on that device. So this LED will be on, sort of, or we can say you have to apply some voltage to turn off this. Okay,
Yes, sir.
so there will be too much of power consumption in that. So do you see from recently the batteries were drained down so fast. Now the batteries are not draining down that fast. That is because of possible because of this thing. Okay, so now
Yes,
what
sir. Yes.
so now
And sir,
what
and sir, and
you
in this picture, you
Mhm.
told that he told that to fix the to increase the ID current
Mhm.
for a fixed VD voltage,
Mhm.
we have to we have to increase the drain a gate current,
Get
gate voltage,
voltage. Get
gate
voltage.
voltage, gate voltage. So this is the turn on process.
This is the turn on process. Yes.
Okay.
If the
Okay.
gate voltage is zero, the current is less. Okay. That is the leakage current. That is the leakage current or the off current.
Okay, sir. Okay.
Okay. If this off current is higher, then the power consumption in the off state is very high. So
Yes.
whenever you see the rating of a device, you can see the off current rating on off or what is the power consumption in the off state that you can see if you
Blocking voltage, sir. Blocking voltage.
yes if
How much
you
voltage is block?
no what is you can say like some of the displays give 20 watts when they are off 1 watt will be consumed when you have turned on the main switch. Okay, when you have turned on the main switch of your TV, let us say TV main switch is on and you have turned it off from the remote. The TV is on, but in the background, it is the all LEDs are turned off by by the transistors because the transistors are at 0 volt. Okay, the transistors are
Yes.
at 0 volt, so the minimum current is flowing through that. Okay, because you have already applied the drain voltage 0.5 volts, right?
Yes, sir. Yes,
0.5,
sir.
this 0.5 into this voltage you have applied multiplied by the current that is going through that. Let us say 10 raised to power minus 9 amps it is flowing. This much watt. Okay, VD multiply the leakage current, get this or turn off current multiplied by this much. So it is the power consumed by single LED. Let us say you have 600 pixels in a screen. That is a very small screen. Let us say 600 pixels multiplied by 600. Okay, how many pixels? That depends on your screen. Huh? Okay,
Yes, sir. Yes,
and
sir.
multiplied by
Megapixel.
that many of pixels with that off state current and the drain voltage that has applied. So that is the off state power consumption.
Okay, sir.
Okay. So that off state power consumption should be very, very less. So when you because in your you have mobile phones, right? Your mobile phone is not off always. You have just turned off the screen. That turned off the screen is because uh, there is always VD is applied always in each pixels. Okay, And that is the
Okay, sir.
off state power consumption. When you have put your mobile in the morning, it was 100%, and in the evening, when you see that it's 90%, the 10% of power consumption is went to turn off the device, just to turn off the device. Okay. So
Yes. Okay, sir.
sometimes people say if you are not using your mobile phone for the whole day, just switch it off. Okay, just switch it
Yes,
off.
sir.
It is not consuming any power. Okay.
Okay, sir. Okay, sir.
Yeah. And now undesirable currents. So we talked about some impact ionization, right? In that case. So uh, here, here in the okay, here. So when you have applied very high voltage at the drain, so okay, at the drain, so it has not only uh, created the drain induced barrier lowering, but what it has created is very high electric field, right? That high, very high electric field. Can you see that thing?
Yes, sir. Yes, sir. It will be seen there.
This thing. Because can you see the slope in this conduction band and the valency band? That slope defines the high electric field. So when an electron is moving in this region, okay, an electron is moving, so it is accelerating because of that electric field, right?
Yes, sir.
So the elect it is accelerated because of the electric field. If it is go the electric field is go beyond 10 raised to power 7, let us say 10 raised to power centimeter per voltage per centimeter. Okay, let us say it is going that beyond. Now there are ions or there are atoms in this semiconductor. Okay, there are atoms in the semiconductor. Electron is moving too fast. Through the electrons are moving, so they will like collide with these atoms. Okay, and because of the very high velocity, they will collide and they will knock off the electrons from these. Okay, so the more number of
Sir,
electrons
sir,
will be generated in this region. Okay, so
sir,
that
how they can collide, sir?
because okay, because there are atoms now in your
Diffusion
semiconductor.
region.
Okay, there are atoms now in this one. This is
Okay,
the
okay.
Venn diagram it is shown. So okay, let us say your drain. This is the barrier down till this point. Okay, so electrons are moving in this direction, right?
Okay, sir.
So here atoms are there, right? In this
Yes,
one.
sir.
So they will collide, these electrons will collide with these atoms and they will knock off the electrons from the valency cell or any of the cells inside the atom. Okay.
Okay.
So more electrons will be generated because of this collision.
Okay, sir.
Okay, so because of that, there will be that is the impact ionization. You are ionizing the atoms with the impact of the electrons.
Okay.
Okay, that is the impact ionization. So you are generating electrons and they will contribute to the current.
Okay, sir.
Hmm. Now, the another thing is, so the electric field is very high, right? So
Yes, sir.
So the electrons, because of the collision with the atoms, they can, let us say this is the atom, electron is coming, it can collide with this one and can go in this direction, anything, right?
Yes, sir.
So due to the collision, so there will be some, this dielectric is there just above the channel, right?
Yes, sir.
So they will be damaging to the dielectric as well. Okay, because
sir.
electrons are going, so they will be damaging the with impact, because they are very high speed, so they will be damaging this dielectric as well.
Yes,
So
sir.
the gate dielectric cannot withstand for longer time. So your leakage current will be high. The the transistor will fail in some time. Okay, in some days it will fail. Okay.
Okay, sir.
Now,
So, sir, if we this can affect on an aging effect, na? If we use this device long time,
mhm, yeah,
there will
age will be reduced.
yes, yes, yes.
Yes.
Okay, sir. Okay, okay.
Okay. So now, okay, now once we get to go to get a substrate or surface. Okay, that is fine. So these are the things that I wanted to tell you about the when you scale down the transistor. So what undesirable things can happen. So if you have any doubts till this point, you can ask
So,
anything.
sir, you can tell the fourth thing is there. One is the uh, your
Drain induced barrier lowering.
okay.
One is undesirable currents, and
One is scaling
one scaling we have done.
and
Okay,
charge sharing between source and
charge
drain. Okay,
sharing
okay,
between source and drain.
okay, sir. That will be clear, sir.
Okay, yeah. Anything else in the previous lectures or something?
No, sir. Uh,
Anyone? So if any, okay, just give me 1 minute. Anyone has doubt? If you have any doubt, you can ask, or we can stop for the today's session here. Can we
sir,
stop?
in tomorrow class, sir, you can take 12 week 12,
What?
week 11 and week 12. This is LED part and your application of power transistor.
Okay, 1 minute. Tomorrow, today is the 12th lecture, and tomorrow is the extra 1 hour class.
Okay, 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 okay.
Okay, so tomorrow I'll just give you a brief about what I will be talking about. Okay, so
LED.
LEDs, about the photo detectors and LEDs, how they will look like if you see the galaxy with the radio waves, infrared waves, visible, ultraviolet, and these are the like images taken with the different photo detectors in the camera. Okay, how the galaxy would look like. So we see the galaxy like this, right? In the
Yes,
visible,
sir.
we are because our eyes are susceptible with the visible rays. So infrared camera can take the image like this. The radio waves would see like this. If we would have the capability of with the radio waves, we would see the galaxy like this. Okay, in X-rays, the galaxy would look like this. Okay.
Okay, okay, okay.
So tomorrow we will see about the solar cells. Many types of solar cells are there: crystalline, amorphous, thin film, CDS.
Okay, okay, sir.
Okay, and then what is the current state of the art?
Efficiency.
Okay, about the solar cells. These are the different type of solar cells, and what is the highest efficiency, and how did they achieve the highest efficiencies? Then we will see the solar spectrum. Okay, this
Okay, okay.
uh, and then we will see the absorption of the photons. So how your this photo detector and the solar cells work. Okay, and what you can do with that. So then how these charges are separated. Okay, if you apply an external force, and how these charges are separated. Okay,
Okay, sir.
and then induced electric fields inside a semiconductor because of the p-n junction. There is a band bending because of p-n junction. So these are the induced electric field inside a phone. So this is the principle of working of a, yeah, of a solar cell. Okay, so we will see these things: solar cell
Yes, yes.
characteristics, current voltage characteristics, and then the uh, short circuit current, how the short circuit current depends on the photon energy and the band gap. Okay, the voltage.
Okay.
So how you can solve that issue, that also comes. Okay, so and this is the photon energy versus the band gap. So the absorbed photons and the band gap. Okay, we will see these things in detail now. Okay, so there are some many things, but we will try to cover it up in one class. Okay, not
Okay,
that
sir.
much
Okay, sir.
required though. So I think these are okay. LEDs I haven't covered. We will try to cover all the things tomorrow. Okay, so these are not that much, but we will try to cover it up. So this was the thing that I wanted to tell you about the
LCD,
LEDs. Yeah, about
LCD scheme, sir.
yes. So these are the color filters in this one. So this is the liquid crystal that orients or that if you apply some electric field, it have you seen the polarizers? Okay, these are the polarizers. Mhm.
The polarizer means, sir, it can pass one kind of rays.
Not one kind of rays, either parallel or something it can
Yes, yes.
go.
Either
Okay.
parallel or vertical.
So there will be one polarizer that will polarize the light in a single direction. Okay. A light comes in all the directions, right? This. Okay. So when light passes, so there is some electric field associated, there is magnetic field associated. So when the light, okay, okay, the wave is such that when it passes through a polarizer, it is either perpendicular or the parallel. Okay.
Okay, okay.
So you can block through the polarizer with the polarizer by like half
Some
of the
kind of field.
intensity. Half of the intensity you can keep do that. Okay, if you put the polarizer,
Yes.
because it will pass only the perpendicular or the parallel, but only per parallel. Okay, it will pass the parallel. If you put two polarizers which are perpendicular to each other, then the intensity you will get is zero. Okay, this is the working principle of that thing.
Okay, okay,
Okay,
okay.
so initially you pass the light through a polarizer here. Okay, it has done the intensity half, or in a single, let us say the perpendicular one only. So when you pass the light with a parallel polarizer, it will be blocked.
Zero, output zero.
Okay, so in this one it will be blocked because and in this one it will be passed. So whatever light come through this pixel will be a mixture of green and this. Okay,
Okay.
the intensity of the light was controlled with this one. How much you need to polarize this one? Okay, the liquid crystal.
Okay.
Okay, we'll see. Green gap and all these things. We will see these things. These are not required. I just added last time. This was the 13th lecture that we will be taking tomorrow. So I have added other some how these um, things, the electronic devices are made actually. Okay. The techniques to make these things. So I have gone through these things. So these are the tools. required for that. Okay. So these are the
Then you can
processes.
teach this in this course,
Yeah, I just,
previous time,
yeah, previous time this was like just an extra things I taught.
for this same course, sir.
Yeah, yeah, for the same course.
Okay, okay, okay,
Mhm. Okay.
okay, sir.
So, and you can go through the lectures, the links are shared, right? So, if you go on my channel on YouTube, so last time lectures are also available. So, in all these things were covered in detail, complete, full detail. Okay, if you find any difficulty, okay,
Okay, sir. Okay. I
yeah,
can mail you, sir, for today's class, sir.
okay, okay.
I think you have got a mail, sir.
Yeah, today you mailed me about that MOSFET and all these things, right?
Yes,
So
sir. Yes, sir.
whatever
Because
part was left, that's why I covered this the scaling. So it was the scaling is really very important for your course. Okay.
okay, okay, sir.
Yeah. So
If anything, sir, required, sir, I can mail you, sir. Okay.
yeah, sure, sure, sure. Okay. So what we have seen all these things, right? So can we stop today, or you have further any doubts?
Yes. I don't know what about other, sir.
Okay. Okay, let's stop here then.
Okay, sir. Thank you, sir.
Okay. Yeah. Thank you for joining the session. So we will see you tomorrow. Okay.
Thank you,
Thank
sir.
you.
Good night, sir.
Good night. Thank you.